Okay, welcome. So what we're going to be going over today is a continuation of the discussion of optics. So start off, the main topic for today, once I can share my notes, is going to be refraction. And refraction basically it can kind of the phenomenon of refraction can kind of be thought about as in just in kind of a simple way. And refraction, what this is the observed phenomena of light changing speeds in transparent media. Now, here's the thing. We are talking about transparent media. So we're talking about things that light can move through, but the light interacts with the material as it goes through it, and that's ultimately what slows it down. Okay. So that's what we're talking about when it comes to refraction. Now, what I want to do is we're going to need to define a couple of terms here. And some of these are things that they're not what I've used before, but I do just want to define some constants that we'll need to talk about. So we'll definitely see this is the speed of light. Now, I did just indicate that the speed of light is going to change depending on what medium it's in. So really, this is the speed of light in vacuum. And as a reminder, that is approximately 3 times 10 to the 8th meters per second. So that's what you're doing. So like 300 million meters per second. Now, the other symbol that we'll use, this V, and a lot of times it will be we'll have a subscript. So I'll just do I for a subscript. This would be the speed of light in medium I. Okay. And a lot of times the speeds they don't come into it. Like we'll connect to the speeds when we do some of these equations. But what I want to start with is I want to start with some of the observed phenomenon. And I'm going to do this with a beam of light, but it turns out this works with solid objects because they're the light you're seeing bounce off of them is kind of subject to sort of the same effects as a beam of light. So this is something you can observe. It's easiest if you have like a horizontal sided tank, so like a fish tank or something. But sometimes you can make this work with like a glass, where if you stick something angled into it, you'll see it appear to bend. And basically I want to show a diagram of that. So um let's call this the observed phenomenon. This is just kind of the simplest version. We're going to go over several other today and in the next class as well. But the idea here is that you would have this would be glass, and then outside would be air. So as a reminder, for air, the it approximately so we'll just say this V sub air is approximately equal to C. Air doesn't interact with it much. The main way that air interacts with it is in something called Rayleigh and Mie scattering. That is actually why the sky is blue. It's a misconception that it's reflected light from the ocean. The sky is actually blue due to Rayleigh and Mie scattering. That's what that's what kind of goes on with that. And yeah, I don't really have time to go into that. It's a quantum mechanical effect. So again, it's somewhat complicated, but that's neither here nor there. So the V of the glass is definitely going to be less than C. Now, the idea here is what I'll do is I'll try and draw these just freehand as straight as I can. But what you would have is you'd have a ray of light. And I'm going to draw my ray of light in red. It could be red light, could be some other color. But basically, when you shine this in, what you would see is you would see it do something like this. So the straight line path I'll do in a dotted line. What you would see is you'd see something like this, where you'd see the path of the light sort of diverge from the straight line path. And then, just draw that straight line path. When it gets to the end, what you would see is you'd see it diverge again and kind of back in the original direction. So it would be kind of going parallel to it. Now, I do need to make the case that these two sides are perpendicular or parallel to one another. Doesn't matter if the other side, if the short sides are perpendicular, but the two edges that the light interacts with, they do need to be parallel to one another. Okay, so the idea is, okay, well, what causes things to do this? And again, like if you have like a chopstick or something, and you just go put it into, a fairly large tank of water that you can see from the side, you can actually observe this effect pretty readily. You can see that the object appears bent when you put it into the water. You may have seen this with like a drinking straw or something like that as well. So the question is, why does the change in C, why does the reduction in light's speed have this effect? Okay. So that's kind of the question that we want to go ahead and answer here. Now, um, I kind of want to do another diagram of this. I'll try and make it a little bit longer and hopefully a little bit bigger. But let's just say we have glass and we're gonna have a beam of light coming in. And like I say, I will try and do it as straight as I can. It's not perfect, but we have a beam of light coming in. Now, the other thing to remember is that not only is this just a ray of light, but there are wave fronts in this ray of light. And I'll just draw them kind of like this. I'll spread them out a little bit. And I'll just draw them kind of like this. And we want to, because these represent the crests, we want to, try and space them out roughly evenly. If I had a ruler, I could probably do it a little bit more precisely, but make them approximately the same distance apart and the same length. Now, the next one here, I can do part of it, but basically some of the wavefront has started to interact with the glass. And the point of that is that now what happens with this wavefront, that portion of the wavefront is now going to travel more slowly. Okay. So basically the portion that's still in the air is just going along as it normally would, but the portion now in the glass is going to sort of fall behind. And this whole idea is that the portion in glass lags behind due to slower speed. Now, what I'll try and do is I'll try and draw the next wavefront. So it would be about there. And now you can see that a lot more of the wave is interacting with the glass. But what you have here is you have something like this. Okay, so now more of the wavefront is lagging behind. And by the time I get to drawing the next one, all of it is going to be inside the glass. But look at what has happened here. A couple of interesting things have occurred. First of all, the wave fronts, you can think of the direction of the ray as kind of being related to the wave fronts, because the ray is perpendicular to all the wave fronts. But because the wave front has changed its orientation, so I'll try and draw the next one. The wave front has changed its orientation now. It is now not going in the same direction. That one's not very good, but try and do it like so. It is now not going in the same direction, okay? What the wave front is doing now is it is now going, what the ray is doing, it's going to be perpendicular to the wavefronts. Try and do that as well as I can. That's not very good. But, oh no. Undo. There we go. The it's going to look kind of like that. Okay. And again, the ray would kind of continue on like this, but that's the straight line path, but the ray itself is bent. And so what we have here is we would have another one, next that looks like this. And we could keep on doing that. So not only has the wave front changed, but the wavelength has also gotten closer together. So this is another thing that is worth knowing. Lambda is reduced in the medium. Now, one thing to know is that the frequency remains the same. Okay. Frequency is constant. And this is worth it's you can kind of see this if you were to turn this into an animation, but because the cycles get closer together, the number of cycles per second stays the same. But when the cycles get closer together, the speed is actually reduced as well. So the speed is reduced via reducing the wavelength, not via reducing the frequency. That's worth noting. But basically what we have here, we'll draw a couple more wave fronts, is that now they're closer together and they're going in a different direction than they were. So again, a little hard to do that, but basically that is what is going on here. Okay. Now, when we get down to the bottom and we have our wavefront like so, and then the next wavefront starts to leave the medium, basically this one speeds up. So at this point, the wavefront, I probably did a little bit excessive there, but probably too much. But at this point, the wavefront has now wavefront speeds up. And so the next wavefront, would look like this with, portion of it still in. And the next wavefront is entirely out. And what we have here is we have this ray kind of continuing on in the same direction that it was. Again, assuming these sides are perpendicular. Okay, so that's or parallel to one another. So that is what is going on with refraction and why it happens and why slowing the speed down why slowing the speed down has this effect of effectively bending the path of the light. You can actually observe this if you had you can imagine this happening. If you had say you're kind of going along you're cruising along a highway, maybe not a highway, but you're cruising along a blacktop road at a reasonable speed, and what you have is you have like a strip of like mud or maybe even gravel, just soft dirt that your wheel can't move as quickly through. If that's angled, if it's perpendicular, you'll experience it as kind of like a bump. But if it's angled, it'll kick your car to the right, because if one heel hits it first, and that say it's your right wheel that hits it first, and that starts going slower, it'll kick your car that way. Same basic thing is happening here with the speed of light. So that's another way you could think about it. Couple of things to note about this. So now I've just drawn this, the kind of what happens, but here's the thing to notice. That in refraction, so notes about refraction. So some things to keep in mind. One, always, and this is not negotiable, measure angles relative to the perpendicular. Okay. When I introduce Snell's law, those and we quantify this. I'm not going to derive Snell's law, but when we quantify it, the Snell's law is expressed in terms of angles relative to the perpendicular. Now, here's the thing. You could for straight line surfaces, you could easily reformulate Snell's law so that it's relative to the surface. However, the problem with that is that it becomes less clear what that means if your surface is curved. Okay, so we define this normal this normal line, a perpendicular line, because that gives us an easier way to approach this. Okay, so same thing we talked about with reflection, how we talked about our angle of incidence being relative to the perpendicular, not relative to the surface. We do the same thing with refraction. Okay, now the point with that is that when going from high speed to lower speed, light bends toward the perpendicular. Okay, so when we went from the higher speed air to the lower speed glass, notice our ray, it would have been it bent towards the perpendicular away from its normal path. Okay, it didn't bend away from its normal path away from the perpendicular. That's what it actually did down here. I'll just continue. When we went from the low speed to the high speed, it bent away from the perpendicular. Okay, so when going from low to high, when going from low to high, light bends away from perpendicular. All right. Now, one other thing to talk about when we talk about refraction is we often, like I say, what we end up dealing with is not the speed of light in the medium. That's not something that's very easy to measure. What we end up dealing with instead is actually a ratio. So we use the quantity index of refraction to deal with changes in speeds. Okay. So again, because even when the speed of light slows down, it's not something we can measure visually. Basically, in terms of our perception, it happens functionally instantly. But what we can measure is we can measure the refractive effect, and from that we can infer the difference of speed of light of the speeds of light. But a lot of times what we'll do is we'll just measure the refractive effect, and if we care about the speed of light, we'll calculate it from that. So the index of refraction. So we'll say n sub I. This is the index of refraction of medium I. And I remember I could be anything. Could be glass, could be air, could be diamond, could be water, could be ice. Okay. And n sub I is equal to the speed of light of I, the speed of light in I, divided by c, the speed of light in a vacuum. Okay. So the idea is that basically what n is, it's the speed of light. I'm sorry, this is flipped. C over v sub I. So it's effectively the factor by which the speed of light is reduced in the medium. Okay. Now, the point here is that these rules for bending, it was high speed. So I'll just indicate this. It's low n to high n. That's what bends you toward the perpendicular. And this is you bend away from the perpendicular when you go from high n to low n. Okay. So the speeds and the indices of refraction are inversely related. All right. So that's something to keep in mind. Now, I do want to, like I said, we could derive this. I'm not going to. It's a little beyond the scope. I don't really want to go through all the trig either. Is that if we had, just our example, and this time I'll draw it once again. It's not so good. And then it goes like so, and then it leaves. And then if we were to measure these things, and that's actually going to be part of lab, let's say that this theta, just call that theta 1, is equal to 45 degrees. We'll call this theta 2. That definitely does not look like 30, but we'll just call it 30 degrees. And notice I am measuring them relative to the perpendicular. Okay. Now the question here is, well, what is theta 3? Well, assuming again that these edges are perpendicular, that we drop this down. As long as they're both, these edges are parallel. As long as they're both perpendicular to the same line, they have to be parallel. So that's fine. But Snell's law states the following. So Snell's law. It states that N1 sine theta 1 is equal to N2 sine theta 2. So if I wanted to find these, I would need to know at least one of the indices of refraction. That's still an unknown. So I'm going to say this is air. For air, n sub air is approximately equal to 1. That's typically what we use. If you're doing really precise work that does involve vacuum, you might change it. But for normal purposes, we'll just assume it's 1. Now, what we have here is we would say, okay, this is fine. Now, the question is, okay, what is N2? Well, we don't know, but we can figure that out. So what we'll do is we'll set this up, and we need to be consistent with our medium. So I'm going to let this side be the air side, and this side be the, call it glass side. It's probably some glass within this index of refraction. But in any event, we'd say, okay, 1 times sine of 45 is equal to N2 sine of 30. In this case, we weren't given N2. We're solving for N2. So sine of 45 is about 0.71. N2, what we're looking for. So multiply 0.71 times 1, you just get 0.71. N2, and then sine of 30 is 1/2. When you solve for N2, this is approximately equal to 1.42. And that, again, means that the speed of light has slowed down in the glass. Okay? So that is what we are seeing there. And then the question is, okay, what then is theta 3? So theta 3 equals, and then we're just going to prove that it should be 45, but we're just going to go ahead and prove that. So we would have N2, which was 1/2. And then we know that this angle right here, that is still 30 degrees. That's just an alternate interior angles idea. You can kind of prove that with just the triangle. Like I'll do the triangle in purple. You can do this triangle right here and prove that this angle would have to be 60 degrees, which means that if you then did another triangle like so, this one would have to be 30 degrees. So still 30 degrees. So sine of 30 degrees. Sorry, that should be 1.42. All right, so theta 3. So N1 sine theta 3. Because N1 is still just air. So sine theta 3. And when you do this, you get theta 3 ends up being the arc sine, because N1 is just 1, of 1.42 times sine of 30 degrees. Okay? When you do that, what you should get is that it's just inverse sine of 0.71, which is then the inverse sine of 0.71. We should know that should be theta 3 should be equal to 45 degrees. Okay? So that's why that's the case. All right. So that is sort of the basic Snell's law problem. I want to go through a couple of other problems conceptually. One other conceptual problem, and then we'll get into tonal internal reflection, which is a which is a much more which is more mathematically oriented. Okay, so I want to talk about a prism right now. So Snell's law and prism. Now, I'm going to talk about a triangular prism, but a rectangular prism is kind of similar to what we just looked at. So we'll just look at a triangular prism and I'll try to draw it if I can. I'm not very good at this, but that's okay. Nobody minds. Okay, so basically, again, it's just like a longer piece of glass that's triangular on its face. So not like a box, but with instead of rectangular bases, it's got triangular bases. And we're going to look at it face on. So we're going to be looking at the triangular portion. That's going to be more relevant to us. Now, being able to show this, I'm going to try and draw it fairly large. Being able to show this, it's helpful if I have the light beam going up kind of like so at an angle like this. Okay. So this will be red light for now. And what we will get here is as a reminder, just kind of see just qualitatively, like don't just again, if this is a glass and here we have air, see if you can just draw some perpendicular lines and just kind of get a qualitative sense of what this thing is going to do. Okay. This is worth checking out just to see if you can figure this out sort of on your own. And sort of how that connects to Snell's law. So I would encourage you to pause and try that. But what I would do if I wanted to understand this, first thing I would do is I would draw a perpendicular at the point the ray enters. And then I would say, okay, I'm going to do a dotted line to kind of show which direction it would go. And what I know is I know it's going to bend towards the perpendicular. Now, it's not quite, it's gonna bend towards that. That doesn't work either. It's gonna bend towards that dotted black line. So what I'm gonna do is I'm just gonna say, well, okay, fine. I'm just gonna draw it more or less horizontally now because that's away from what it did and it's toward the black line. So that's great because it's going from air to glass. So the glass has a higher index of refraction, slower speed. As a reminder, when that happens, we bend towards the perpendicular. Okay. Now, what's interesting here is the second surface it encounters is not parallel to the first surface. So we can't just say it's going to correct its original path. We actually have to break out another perpendicular line. Okay. So I'll draw another perpendicular line like so. And I'll do this in dotted red again. The normal path would be like this, but this time we're going from glass to air. So the opposite thing happens. We don't bend toward the perpendicular line, we bend away from it. All right? We bend away from it. Now, the ultimate example of this is that functionally this has changed the direction of light. Now, the net effect of this is that you get very weird it's not at all when you're looking at objects through light, it's not at all clear what you can see on the other side. So a lot of this does have a distorted effect. You can see this in a lot of decorative panes of glass. You look at the edges are beveled. So the edges are the most of the glass might be flat. You see through it fine. But if the edges are slanted, you really can't see through that part at all. And that's because you have this distorting effect where any of the light that goes through the edge, like this, gets distorted in this way. Okay. So one other thing I wanted to show is what happens if you have multiple colors. Now, there are a couple things to know. First of all, white light is a mixture of colors. And the way this was actually proven is a mixture of colored light was actually with a prism. Now it's a super interesting experiment to be able to do that. But this it's a little bit on the scope of what I want to talk about now, but you've probably heard this phenomenon before. But white light is a mixture of colors. Okay, so that's one thing to note. Now, another interesting thing is that index of refraction is frequency dependent. Now, what does that mean? Well, it means that different frequencies of light experience different indices of refraction in different media. So what this means is as F increases, light, N increases, N sub glass increases. Okay. And this is actually really fundamental to why this works. Okay. So I want to show this. Kind of like so. And what I'm going to do is I'm going to we'll just do three. So, whoops. I'll have them all parallel. And I'm going to do them all really close to going in at the same angle. So the way you could think about this, you could think about this as being a beam of white light, where I'm just going to draw red, green, and blue, kind of right next to one another. But we're going to say they all sort of enter at the same spot there. Now, what we saw, I'm not going to draw the perpendiculars, but what we saw is that the red is going to bend, it's going to bend away from the perpendicular, like so. Now, the issue with having the index of refraction in glass greater for red light, or for green light rather than red light, is the green light bends more. Okay. Now, not a whole lot more, but and it's exaggerated in this case. You wouldn't be able to see this, but the idea is that they enter at the same point, but they don't exit at the same point. Okay. They're going in a slightly different direction. Same thing with blue. All right. They enter at the same point, but it doesn't exit at the same point as either the red or the green. So what like I say, I'm exaggerating it, but what you can see is that just due to the fact that the index of is greater for the blue light than the green light than the red light, and I'll indicate that down, N sub R is less than N sub G, which is less than N sub blue. Okay. Now, interestingly enough, the same thing happens at the other surface, is that the red light, it does bend down this way, but the green light ultimately bends more because it's got a larger change in the indices of refraction. Same thing with the blue light. The blue light bends more. Now, again, it looks like in this diagram, it looks like you would be able to see this. You can't really see it on the scale, but the fact that they're heading in different directions means that if you let the light move for a little bit, you will actually get a substantial separation. This is how you can use a prism to turn white light into rainbow light. And you may have seen this again if you have little panes of glass with slanted bevels. Those do act like partial prisms, and they will kind of separate light, make these cute little rainbow things. So basically, the colored light gets separated. All right. So your white light gets split into colors. Now, that's not the only way to do this, but the white light gets split into colors. Now, this will happen. This will happen if you have oddly shaped indices of refraction. So if you've ever seen just those sort of glass solid structures with numerous facets, they will all generate a separation of light to some extent or another. There are other ways to do it, but there's a certain sense in which lenses do this as well. We'll talk about lenses later. That has to do with a curved index of refraction, which is quite cool, but we'll talk about that soon. Probably in the next class. Definitely in the next class. But the whole point is that this separates the different colors. Okay, so this is why this is how this phenomenon will work. All right. So that is ultimately how this thing is going to be. And you, like I say, you could do a calculation with this. You'd have to know the different indices for the different colors, but ultimately this is qualitatively what's going on. Now, the last thing I want to talk about is total internal reflection. Now, what I'm going to do is I'm just kind of gonna pose an example and say what we have here is we have just a long piece of glass. Now, one end is right here. The other end, for the most part, the piece of glass is just going to continue on. Okay, so this will be glass, and then outside will be air. So again, the whole idea is that n of the glass is greater than n of the air because the speed of light in the glass is slower. Now, what I want to do is I want to say, okay, what happens if you shine a beam of light like so? Okay. So my question is, what is going to happen? Now I'll try and draw this a little bit more exaggerated. But let's say that this theta, I'll just say theta equals 20 degrees. Okay. So what is going to happen there? All right. And you can and what's interesting about this is again, you might say, well, if you get the light straight on, then it would just continue on the glass just a little bit more slowly. But I'm not getting it straight on here, okay? It is angled, like 20 degrees is pretty substantial. It's not hugely substantial, but it's enough. So the question is what happens? Well, hopefully you can say this, okay, at a qualitative level, if the normal path would just do that. What the actual path is going to do, it's going to be something in between the normal and the path I just drew. Okay. So then the question is, all right, we're going to call this theta 2. And go ahead and do a quick calculation of theta 2. I'll give you the index of reflection of the glass. We'll just say n of the g is equal to 1.5. And if we do that, we get, n of air is 1. So we get n1 sine theta 1. Now, theta 1 in this is equal to 20. You will need to keep track of your own indices of refraction. Sometimes they'll just give you angles, and you don't want to use the wrong angle, but you also so you need to keep track of which angle is which. Okay, so what we end up here is we end up with n1 sine of 20 is equal to n2 sine of theta 2. That's going to be sine of 20 over 1.5, and we'll take the inverse sine of that. Should give us theta 2. Hopefully, what you will see, if you're in degrees, you will get 13 degrees. Now, make sure you're in degrees. This is another common place where people are in radians. It screws everything up if you're in radians. It's no good. Okay. So that means, okay, so it's 13 degrees. So basically in this angle right here, we have 13 degrees. Now, the better question is what happens at the next surface, because we can already see what I've drawn here. The light is eventually going to interact with the next surface because this thing is quite long. Now, we need another perpendicular. Now you notice, hopefully you will notice that okay, we're really close to, like this angle right here. It's really close to the surface, which means that our angle relative to the perpendicular is high. Like this angle right here is 77 degrees. Okay, just doing it to the nearest degree. The question is, what happens now? What will happen when the angle exits? Now, if I were to try and draw that, like if the normal line is going like this, I'd have to do something like this in order to make it work. Now, what's interesting, sorry, that wasn't the normal line. This would be the continuation of the path line. So the question is, okay, what happens there? What is the angle? Well, the idea now, what we can do is we can say, okay, n of glass sine of 77. All right. Because again, it's not going to be sine of 13 because we care about the angle to relative to the perpendicular. And we're at a different side at this point. So we got to change that angle to the 77. Should equal n of air sine of whatever angle. I'm just going to call that theta sub O or theta out. Now, when you do this, what you'll get is you'll get 1.5 sine of 77 is equal to sine of theta O. And then you get theta O is equal to inverse sine of 1.5 times sine of 77. And if you try to do this, you will find your calculator won't give you an answer. The reason why is that sine of 77 is really pretty close to 1. It's, I don't know, it's like 0.97 or 0.96 or something like that. So sine of 77 is really close to 1. You multiply that by 1.5, you're going to get something greater than 1. You can't take an inverse sine of something greater than 1. Okay, you can't take an arc sine of something greater than 1 because sine is only ever going to give you something between -1 and 1. So if you try to do an inverse sine of greater than 1, it's going to give you an error. Okay, so theta O does not exist. Now, the ultimate reason for this, it's kind of difficult to explain, but basically the light is going too slow to emit out of the medium. Some of it might be absorbed by the medium, but for the most part, the light is just going too slow. Now, what does this mean? What does this imply? What this implies is that all light will reflect. Okay, so at that situation where you can't calculate a refracted angle, that means that you're back to the only other option you have for the light to do is for it to reflect. Okay, so in that case, what we get here is we end up with, okay, that angle is going to be 77 degrees, and we end up with the light bouncing off this way, like so. Now, when we get to here, we're going to have the exact same problem again, assuming again that these two sides are parallel, but we're going to have another 77. And this means, okay, well, all the light, we're going to have the exact same math problem to figure out what angle it leaves at. So all the light reflects again. So again, we just get this thing. And this thing will occur indefinitely until, as long as these sides are parallel. It gets to the end, and, it finds something it can actually refract through. Then it will leave. But for now, the light is basically stuck. Okay, it's basically stuck inside the glass. This is how fiber optics cables work. Okay, you shoot light at a slight enough angle relative to the side to the edge of the cable, and you will get total internal reflection. And you can send light signals down miles and miles and miles of these fiber optic cables. Okay, so fiber optics are not sending electrical transmissions, they're sending light transmissions. Okay, and they're doing it via this phenomenon of total internal reflection. Okay, if and the whole idea is that without total internal reflection, you would lose signal because some of your light would refract out. But as long as you're ensuring that physically the light can't refract out, basically it's going too slow to leave the medium. Physically, the light can't refract out. All it can do is bounce off the edge there. Okay, so it bounces off, and it will keep on bouncing off until it encounters a surface that it can actually refract out of. Okay, and we call this phenomenon total internal reflection. All right, and a couple of things to know about total internal reflection. It only works if going from high N to low N. And again, N being the index of refraction. Okay, it won't work otherwise. Okay, now the idea here, the way this is stated mathematically, is that I'll just call it. I'll do a abbreviation TIR. I'm not going to write total internal reflection each time. TIR occurs if theta incident is greater than or equal to what we call the theta critical. Actually, I'm going to go with greater than. If it's equal to the critical angle, then that light is actually lost. It actually does leave. It kind of leaves parallel to the what occurs at the critical angle is interesting. I'm not going to go into that. Where theta sub c is what, like I said, we call that the critical angle. Now, the critical angle is basically the way you can think about the critical angle. This is the angle that would cause a refracted angle of 90 degrees. So the whole point is that the maximum angle that this thing could be refracted at would be 90 degrees. Like 90 degrees away from the normal, that would be parallel to the surface. So if you had that refracted angle, then your light is just going parallel to the surface once it leaves. Okay, so it's kind of right on the cusp of being able to leave and go its own way, and right on the cusp of having to bounce back. Okay, so the way you would find the critical angle is you would have your N1 sine of your critical angle is equal to N2 sine of 90 degrees. Now, as a reminder, sine of 90 degrees is just 1. So you end up with your sine, once we rearranged, sine of your critical angle is equal to N2 over N1. Now, it's important to remember that N2 is the low index and N1 is the high index. Okay? This is not going to work if N2 is greater than N1 because you're not because then you're going to fall into the same trap where you're trying to calculate a critical angle of for a sine where the sine is resulting in something greater than 1. So it only works if N1 is greater than N2. So N1 greater than N2. Okay. So that is something that is worth remembering there. All right. So that is basically all that I wanted to talk about. This kind of covers the basics of refraction. We'll get into next time we'll get into refraction with curved surfaces, and this is where the idea of lenses comes in. The idea of lenses comes in. And I think that is super interesting, but we will leave that for next time. Okay, thank you for joining me. I will see you in the next lecture.